very similar to our own Milky Way, you can see that there's even on this small scale, there's a huge abundant substructure. And so one of the main reasons that we have this abundant substructure is the shape of the power spectrum. So power spectrum is very flat. So this is the dimensionless power spectrum, which tells you roughly how much variance there is in each logarithmic bin of spatial scale. Here on the top axis, you can actually see what mass scales these spatial scales roughly correspond to. So whenever this power spectrum is bigger than or order of unity, then we expect structures to form at that scale. So you can see, for example, for a WIMP dark matter model, we expect the largest structures to form at like 10 to the 15, 10 to the 16 solar masses. It goes all the way down to like 10 to the minus 6 solar masses or so, where like we have like parsec scale Earth mass halos. And of course, we actually don't really know what is happening on these small scales because we never measured that clearly. So there are, of course, a large variety of things that are still possible in the dark sector. So, for example, it could be that dark matter is actually arbitrarily cold, and we have this black dashed line where you even get structures on even much smaller scales than Earth mass halos. Or it could
Sorry,
be
James. Sorry to interrupt. Now you are the co-host so that you can share the video.
okay. Uh, do you see me?
Yes, perfect. Yes, thank you.
Great.
Sorry.
Okay. So if dark matter is warm, then it might actually be that its thermal velocity dispersion suppresses structure formation beyond a certain scale and smooths out the density field so that we don't get like the full range of structure formation. And to just give you an idea how that looks in practice, I made a small video of a simulation for you. So in the top, you see a warmer dark matter model, and at the top, a colder dark matter model. And you can see that in a warmer dark matter scenario, you actually form structures a bit later, and the density field is a lot smoother so that you form much less small scale structure than in a cold dark matter scenario. And so uh, like whether these kind of small structures exist or not, that's actually one of the strongest probe of the nature of dark matter. So one very important thing to note here is that we don't expect all of these subhalos to form a galaxy. So some halos will form a galaxies, but others won't. So there's roughly a threshold where galaxies only form in halos more massive than around 10 to the 9 solar masses, because only then is cooling of gas efficient enough to create stars and so on. And if you have lower mass halos, we don't expect them to be bright at all, but just to be dark substructures. And whether these dark substructures exist or not is, of course, a very strong probe of the nature of dark matter. So to give you two examples how we might actually be able to test their presence is on the one hand side, gravitational lensing. So here you can see a gravitationally lensed galaxy. You can see that there's this long Einstein-like ring-like arc. And you can see there's this little galaxy G4, which actually puts a strong perturbation to this lensing arc. And you can imagine that the shape of this perturbation actually tells a lot about what's the mass of that structure and its properties. And so this we not only expect for bright galaxies, but also for dark substructures to happen. And we might be able to detect halos as little mass as 10 to the 6 solar mass or so like that. Another very promising probe of dark substructures are gaps in stellar streams. So the Milky Way satellite galaxy gets tidally disrupted. It actually forms like these long stellar streams. And if a dark substructure would pass by this stream, it can actually create a gap in the stellar stream and leave kind of a signature. So we could have a signature of dark substructures like that. And both of these methods are very promising and could tell us about dark substructures as small as maybe 10 to the 6 solar mass or less. And to constrain then the nature of dark matter, right, we need to kind of, on the one hand side, like the observations of these things, right, like the smallest galaxies or gaps in stellar streams, perturbations in gravitational lenses, or maybe also other probes like dark matter self-annihilation. And on the other hand side, we need to combine that with accurate predictions of what is the abundance of these structures So we can use for that cosmological simulations or idealized simulations and analytical tools. And actually want to in this talk focus a bit on the right-hand side of this problem. So how can we predict accurately what is the predicted amount of structure? So arguably one of the most powerful and also simplest approaches is to run these cosmological n-body simulations. So yeah, I show you on the left side a variety of possible dark matter scenarios we might imagine. So you can see the suppression in the power spectrum versus the cold dark matter power spectrum. You have the thermal relic warm dark matter, resonant sterile neutrinos, decaying sterile neutrinos, or fuzzy dark matter also produces a cutoff in the power spectrum, or these ethos models we also heard about yesterday. And I'd say like at first order, we might actually just understand this as something which has like a scale of a cutoff and there's a slope of the cutoff. And we can actually very efficiently probe this to dimensional dark matter space with simulations. You can see on the right a bunch of simulations that I've run in the past for parameterizing what happens with the mass function in all these scenarios. And you can see here what one might expect actually to happen. So if you just vary the scale of this cutoff, then you basically shift the mass scale at which the suppression happens. So this is the warm dark matter mass function or the non-cold dark matter mass function over the cold dark matter case. And you can see that depending on the scale of this cutoff, you get a different scale of the suppression of the mass function. Or you might vary like the slope of the cutoff, and you can see then you get mass functions that extend to much lower masses or less low masses, depending on how sharp this cutoff in the power spectrum is. And so we can actually get very simple and flexible models for parameterizing this difference between all dark matter models. And in principle, I think we should try even like constraining them a bit all at once. But so there's a very important distinction I need to make here on the side of theoretical predictions, and that is the distinction between field halos and sub-halos. So like field halos, it's very easy and to get these predictions, and we can get them very accurate, very simply. But it becomes a lot more complicated if we want to make predictions of sub-halos. So I want to discuss a bit whether we can really reliably predict what is happening with subhalos and what is their abundance and so on. So one very important thing we have to understand for that is tidal stripping. So here you can see some halo that is falling into something like the gravitational potential of the Milky Way's halo. And you can see that immediately it gets tidally deformed and it forms like this two tidal streams, and it gets stripped a lot of its mass until after a significant amount of time it approaches like a more or less stable remnant, which only further loses slowly mass. And so if you look at what this structure looked like in the beginning, it had maybe 10 to the 9 solar masses, but after some time it's just stripped down to 10 to the 8 solar mass, so it has gone down a factor 10 in mass. And you can also see that kind of only like the dense center of the halo remains after some time. And now, do we actually resolve this tidal stripping process reliably in n-body simulations? And here I want to show you an image of one of the highest resolution n-body simulations we've ever run. So this is the Aquarius simulation, which resolves the something like a Milky Way like dark matter halo with 10 to the 9 particles. So that's a huge resolution. On the right side, you can see the total amount of mass that is in substructure as a function of radius in the Milky Way like halo. You can see, for example, that around the Viri radius, like around inside of the Viri radius, 10% of the mass is in substructure. And you can see here different resolution levels, and they all roughly agree on what's happening inside of the Viri radius. And then you go to smaller radii, and you can see that actually becomes a lot more complicated, where now suddenly having a low resolution gives you a very wrong answer on what is the amount of substructure you have than having a higher resolution. And if you go to the central regions, even like the highest resolution versions disagree by a factor 2 or 3 on what is the amount of substructure we might find there. So, and this is actually really relevant, right? Because, for example, if we want to probe dark matter with stellar streams. Those stellar streams are all more or less in the central 20 kiloparsec of the Milky Way. So if we want to predict their perturbations through dark substructure, we need to understand how many of these halos exist at these small radii. And one very nice plot that illustrates well what is the problem here is from this paper from Rafael Irani from last year. So here you can see, like let's say you run the Aquarius 4 resolution level and see how the mass of halo gets stripped over time. And you can see if you run an n-body simulation at this resolution, it actually at some point just disrupts. But then increase the resolution by a factor 8, and you can actually resolve this mass loss a bit further, but then also disrupts. So you increase another factor of 8, and still soon after it will disrupt just at a bit lower mass. And so the problem here is that the conversion is very, very slow of resolving the stripping process. So each factor of 8 in resolution just gives you a little bit of extra time that you resolve the structure. So actually one interesting article to mention is by Frank van den Bosch with a provocative title, Disruption of Dark Matter Substructure, Fact or Fiction. And Frank actually argues in this article that maybe almost all of the disruption of dark matter halos we see in simulation might be just an artifact, or that we don't have enough resolution to resolve the full structure of them. So you kind of have to be careful with the convergence of these simulations at least. Now, so if you think this is a bit problematic, that actually gets a lot worse. And so the reason it does is that n-body simulations actually don't have a realistic tidal field. So if you check, for example, what is the dark matter halo of the Milky Way, you see the tidal field as a function of radius, and can see this blue line as the tidal field of the dark matter halo of the Milky Way. But now if we add the baryonic components like the galactic disk and the bulge and so on, and get actually like something like this orange line as a tidal field. You can see that at large radii, like of course the baryonic components don't matter, and the n-body simulation will give you reliable results on this large scale. But if you go to smaller radii, like 20 kiloparsec and less, then actually the baryons dominate the tidal field, and we would get a very wrong tidal field if we just assume the n-body simulations were correct. And so this actually gives you a huge effect on the dark substructure that you would see in the simulation. So, for example, like a very nice example is given by these Fat Elvis simulations from Kelly et al. In 2019. Here on the left, you can see the substructure that we would see in like a dark matter only case. Whereas on the right, you see what happens if you just add the galactic potential, the potential of a galactic disk. You can see there's a lot less substructure, or at least the substructure has a lot less mass and went to a lot more stripping because of the enhanced tidal field. If you look at this quantitatively, here on the right-hand side, you can see the number of structures that are above a certain mass. And you can see that if you look in the central 20 kiloparsec, if you would take just the results of an n-body simulation, it might be wrong by a factor 10 or so on the abundance of these structures. And even if you just go to 50 kiloparsec or so, it could be still a factor 2 or 3 wrong. So therefore say, predicting the substructure of a Milky Way with n-body simulation is actually quite difficult because of tidal stripping. So to get it right, we need extremely high resolution, and we need to properly account for baryons, which is a bit difficult, right? So like pure n-body simulation, we cannot really trust at below 50 kiloparsec. And I think to kind of resolve this mess a bit, would be really nice to get kind of a bit good theoretical understanding of tidal stripping. And it's also desirable to have analytical approaches available so that we can kind of extrapolate the beyond the resolution of what we have in simulations, and also to correct for like the missing resolved physics, maybe like baryons in n-body simulations, or maybe even to correct hydro simulations at cases where we don't resolve some components properly. So I want to just do that in the rest of this talk to give you a theoretical understanding of tidal stripping. So the question I want to start with is, so why does tidal stripping happen? And like a very good starting point for understanding that is to have a look at the gravitational potential close to our substructure. So this is the gravitational potential of something like the Milky Way halo plus our substructure we're interested in. You can see that there's like an overall like big gradient in the potential, which just tells us that this structure is getting accelerated by the Milky Way. And so one thing I'd argue is that actually we have to remove this gradient from the potential landscape to understand what's happening, because it just tells us our structure is getting uniformly accelerated, and we should move into an appropriate reference frame by subtracting this acceleration. So in that case, we get this thing which I call the boosted potential, and that's roughly the potential as the subhalo experiences it. And so there's now one additional notion I need to explain you, and that is the tidal tensor. So we take the external potential of the Milky Way around maybe a location of interest where our subhalo is, then we could actually do the following. We just say we make a multiple expansion of this potential to get an approximation of how the potential looks in the surrounding. So that means we take the potential plus the gradient times x plus the Hessian of the potential times x. And so now, from what I already told you, you might already immediately guess that actually we can just immediately throw away like the potential at this location and the mean gradient. And then the first term that it really matters is the second derivative. And that's what we call the tidal tensor. And this kind of the potential landscape of that looks actually like this on the right, like so like a archetypical saddle point shape. And so one of the main approximations we need to do for doing something analytical with this is that we say we have the self-potential of our substructure plus this tidal field term. And that's actually a really good approximation to the actual potential landscape in the surrounding of our structure. So in practice, this actually almost always works if you have like a substructure that's a lot less massive than your host structure. There's actually interesting theoretical consequences, like, for example, that the tidal stripping has to be mass invariant if this is correct. So now you have these particles that are moving in this potential landscape of self-potential and this tidal field term. And this tidal tensor, of course, changes over time because your substructure is moving along an orbit. And so you can see, for example, how it looks when the Milky Way is on the left side of it, and then maybe you orbit around it, and the Milky Way is here, and orbit around, Milky Way is here. So the tidal field changes over time, and you have this time-dependent potential that your particles are moving in. And so the subhalo's orbit and the host potential, they basically only matter as far as they determine this tidal history, so how the tidal tensor changes over time. Now, I want to give you a bit an intuitive impression how that looks in practice. So here you see again like a halo that is orbiting around something like the Milky Way. You can see on the right side how the potential is changing over time. So you can see that when the halo reaches the pericenter of its orbit, so the closest point, it's a very large tidal field. When you move farther away, you get a low tidal field for a longer amount of time. You can see that particles tend to escape through this kind of saddle point directions, then forming these tidal streams. Why does tidal stripping happen? So I think the first reason I put forward is basically that we have this saddle point in the potential. So if imagine you have a halo in the vacuum that has maybe some potential and an escape energy. But if you now put it into a tidal field and you press down the energy levels and you have this reduced escape energy level at the saddle point level, and now all particles are above that energy level can escape the system. So the second reason that tidal stripping happens is that having this time-dependent potential landscape actually injects energy into the system. So the impulsive limit, one can actually estimate that easily by saying that the change in velocity is roughly given by the time integral over the tidal tensor times x. So that holds when the tidal field is changing very rapidly. And so if you have this rapidly changing tidal field that injects energy into your particles, then particles which are raised beyond the escape energy level of your structure will also escape the system. So the third reason tidal stripping is happening is actually that mass loss facilitates further mass loss. So if you have the mass of your structure going down, that means also that the attractive potential of your structure is going down, and the escape energy level will be lower, and some additional particles may escape. And so you can see there's a bit of like a vicious cycle going on here. So give you an intuitive example why that is really important. So you can see an example of a potential landscape of an r to the minus 1.5 power law profile. So it's a dashed line. The blue line is what you get so the solid blue line is what you get when you add the effect of the tidal field. And you might say here, okay, if I check this energy level, it's like 0.75, and 24% of all particles are bound to this still, and I just remove the rest. And now you have this feedback loop. And if you go actually all the way through this feedback loop until it kind of converges, you find that you only get a stable remnant at a much lower level where only 1.4% of the initial particles are bound to the system. So you can see that there's like more than a factor 10 in difference in predicting this just from the initial potential or what happens after going through this nonlinear feedback loop. And I think this is one of the main reasons why it's very difficult to come up with good analytical models of tidal stripping. So just to give you a bit of intuition, what can all happen in the potential of like a Milky Way galaxy, for example, I will show you a few tidal histories. So this is, for example, on a circular orbit, the two components of the tidal tensor and how they change over time. You can see you just have this very regular oscillation on a circular orbit. And in this case, actually, we have like a very big effect from this saddle point level or the tidal or Jacobi radius, you might also say, and a very weak effect of energy injection. Actually, there's conserved energy. So we have a non-circular orbit, actually a lot more complicated. You can see you have this weak tidal field a long time in the orbital apocenter, the strong tidal field over a short time in the pericenter. And then you also have some degree of energy injection. And a lot different it looks when you take something like the tidal field of a galactic disk. So in the galactic disk, you have a very, very large tidal field in a very small region of space when you cross the galactic plane. You can see that in the tidal field, it looks actually like you have a very weak tidal field for most of the time. Then you go through this very, very strong tidal field for a short amount of time when a substructure passes through it. And you get this almost like delta function, like shapes of the tidal history. In that case, you have a huge amount of energy injected into your structure, and you have tidal shocks. So very interesting example of what can happen is the case of the stellar encounter. So for example, if you take an Earth mass dark matter substructure and it flies by a star, then it will also have a large tidal field over a short amount of time. And that has, again, a huge energy injection effect. Yeah, so you can see there's a lot of different things that can happen in tidal stripping. And so I want to give you a bit of perspective how we can maybe get a bit of an analytical handle on these different cases. And so for that, I want to once consider like a very artificial tidal history. So that is, if we just imagine we just took a tidal field and we slowly increase it over time. So can see an example of that here. So I just take an NFW halo and I slowly increase the tidal field, and over time, and you can see that there's now most particles that are above the saddle point level, they just escape the system, and you're just left with some kind of stable remnant. And if you do this increase slow enough, then the reaction of the structure actually becomes adiabatic. And I just want to make one further simplification. That is like, I just assume like a spherically symmetric tide. So one that has the same largest eigenvalue of the tidal tensor, so that it actually gives a very similar result, even although the geometry of this is of course a lot different. So if we look at how this looks in phase space, so I made this little movie for you where you see here on the y-axis the radial velocity, and on the x-axis the radius of a lot of different particles that are orbiting with the same peri or apocenter. And you can now I'm increasing the tidal field, and you can see that some particles start escaping because they cross beyond the tidal radius. And in the end, we might end up with some kind of stable remnant, as you can see here. So one important thing that happens if you put this slow deformation through the tidal field onto your system is the conservation of actions. So the radial action is just given by the area of these orbits in phase space. So, and if you deform the system, right, through this external potential from the tidal field, you can see that this area deforms in a very particular way, actually. So you can see that kind of gets stretched along the spatial dimension and actually compressed in the velocity dimension. But the size of the area actually stays conserved, and that is exactly the conservation of actions. So actions are conserved for adiabatic transitions, and that actually allows us to calculate what happens analytically, because the phase-space structure will also be conserved. So that means the final phase-space structure will be the same as the initial one in units in terms of the actions for all bound orbits. For all unbound orbits, actually will be just 0 or undefined. And so I cannot guide you completely through the analytical calculation, but I can just show you that it works. So this is a density profile over the initial profile for different cases. So here the blue, green, and purple line show you what you get if you do this case actually in a simulation. So you just take an FW halo and you slowly add the tidal field, and you can see what comes out. And these black dashed lines are what I can calculate analytically by assuming the conservation of action. I can see that this case actually matches perfectly, just with the difference that the analytic calculation is extremely cheap, and you can resolve it up to arbitrary small radii beyond what you could usually resolve in a simulation. And to give you a few examples of what we can predict with this simple model in the adiabatic limit. So this is, for example, the amount of mass that is bound in our NFW halo as a function of the tidal field that we put. You can see if I put a very small tidal field, then the halo is very robust to the strength of the tidal field, because we're truncating it this r to the -3 regime, where increasing the tidal field a bit doesn't change much how much mass will be bound. But if you put a very strong tidal field, then you truncate your NFW halo in the r to the -1 regime, and then a small increases in the tidal field lead to huge increases in mass loss. So for example, I increase the tidal field by a factor 10, and then I lose 10 to the 4 times the amount of mass. You can imagine that this is a big problem for simulations, and I think it's one of the main reasons there. It's so difficult to resolve tidal stripping, because it has a very strong effect when you truncate your halo strongly. And one thing that is also in this plot, but which is a bit hidden, is the fact that if you increase the concentration of your halo, so you make it more dense, actually you just move on the y-axis to the left in this plot. So you just make it a lot more resilient to tidals. So there's actually an exact degeneracy between tidal field and concentration in this case. And so I want to give you an example how you can use this in practice. So this, like one thing we might state is that if you have this orbiting structure, then the particles that will remain in the long run are the ones that are safe from the pericenter tidal field. So that's when the tidal field becomes the largest. And if I now plug in this pericenter tidal field into this adiabatic model, then I get predictions for the amount of mass that stays bound even in the long run. So this is the green dashed line and the red dashed line here. So that is if I just plug in the pericenter tidal field into the model and check how much mass I'd expect to stay in the long run. And these different lines here are different halos in the simulation that are on different orbits with different apocenters, but with the same pericenter. And you can see that after a long number of orbits, like 10, 15, 20, they all roughly approach a similar limit. And in the red case, like a different limit, because there's a different pericenter tidal field. You can also easily now understand like what is the effect of variance. So I think I'm already almost over time, so I just go over this very briefly. So this is kind of the amount of mass loss that we predict if we have different pericenters or concentrations in a Milky Way with just an NFW halo. Now, if I add the effect of the galactic disk and so on into the tidal field, you can see that I would expect a very different amount of stripping, even going up by a factor of 100 for subhalos that are on the same kind of orbit, the same kind of concentration. So factor of variance is huge. Yeah, I just want to briefly mention an outlook of where I want to go with this in the long run. And so I want to really create, in the long run, a general analytical model of tidal stripping. So what I imagine there is that we should be able to kind of put in any kind of structure into my initial conditions, like an NFW halo or prompt cusp, a dwarf galaxy, or globally large cluster. So that's the initial condition of our profile. And we want to combine that with any possible type of tidal history, right? Of a circular orbit, non-circular orbit, galactic disk, stellar encounter, and so on. And the model should take these kind of two inputs and be able to predict the remnant structure reliably, with including the phase-space structure, the mass loss history, the density profile, J factors, and so on. And yeah, I think this would help with a lot of different things. So just briefly to mention, so I think it would help us understand tidal stripping, alleviate these confusions about disruption I mentioned earlier, helps us extrapolate simulations to unresolved regime and to correct simulations without variance for the baryonic effects. And in the future, I'd like to use that for doing kind of comprehensive predictions of the substructure all the way to Earth Mars halos. And yeah, I think there's plenty of possible applications of that. I'd be, of course, be thrilled if you tell me of whether you have an interesting use case for that. Yeah, I think that's it. Thank you.
Thank you. Thank you very much, Jens, for this very nice talk. So you have a couple of questions in the Padlet. It would be great if you go there and then try to answer these.
Okay.
Thank you once again. So let's move on to the next talk by Ethan Nadler, who is based in University of California, San Diego, I believe. And Ethan can tell us about what can dwarf galaxies reveal about the nature of dark matter, please.
All right, thanks for having me. Can you see my screen and hear me?
Yes.
All right, great.
Yeah.
Yeah, so as Shinichiro has said, I'd like to give you a fairly broad overview of what we can understand about fundamental dark matter physics using dwarf galaxies. This is a really very exciting topic right now, particularly given all of the data that's going to be coming in the future years in this area. Okay, so I want to start just with some motivation. This was already motivated nicely by Jens in the previous talk. But, you know, basically, why are dwarf galaxies so interesting for studying dark matter physics? If we run a simulation, let's say of a Milky Way-sized halo, similar to what Jens was showing in the previous talk, in a cold dark matter model where the dark matter only gravitates, then the dark matter clumps into halos and subhalos down to kind of arbitrarily small scales. Whereas if we change the microphysical properties of dark matter, so in this particular example on the right-hand side, it's the same halo that's being simulated, but now in a sterile neutrino dark matter model rather than cold dark matter, then the abundance of these structures and substructures around the Milky Way and their density profiles change. And so this affects predictions for the number of dwarf galaxies in the universe and also their properties, for example, their stellar density profiles. Checking the chat. Okay, just making sure everything's okay. Okay, so in this talk, I want to kind of differentiate the kinds of dark matter physics I talk about into two broad categories. So I'll refer to these as ab initio dark matter physics on the one hand and in situ dark matter physics on the other. The idea being that ab initio dark matter physics mainly changes the initial conditions for structure formation in the universe, while in situ dark matter physics actually changes the dynamics of structure formation inside of halos and galaxies. So some examples of dark matter physics that mainly change the initial conditions, for example, are the dark matter production mechanism, like in the case of cold versus warm dark matter that I showed you, interactions with the standard model, so kind of scattering between dark matter and standard model particles. I'll actually show you that this is well described by a change to the initial conditions. And to an extent, changing the particle mass of dark matter, for example, making it ultralight, can also change the initial conditions for structure. Now, on the other hand, we have examples of dark matter physics that change the dynamics. So, for example, dark matter self-interactions that transfer momentum between dark matter particles change the process of halo formation and evolution. If the dark matter can decay with a lifetime that's comparable to the age of the universe, this also changes the dynamics within halos. And once again, the particle mass shows up here because if the dark matter is extremely light, then it kind of behaves dynamically more like a wave than a particle on dwarf galaxy scales. All right, so let's see why dwarfs in particular are interesting for studying this kind of physics. So here's a plot of the dimensionless linear matter power spectrum as a function of the wave number k. So large scales are on the left-hand side of this plot, small scales are on the right-hand side. And in a standard cold dark matter model where the dark matter only gravitates, then the prediction is this kind of gray line that extends and it increases in power toward, like I said, arbitrarily small scales. So this linear power spectrum sets the initial conditions for structure formation. In particular, models of dark matter that suppress the power spectrum produce fewer halos and subhalos on the corresponding mass scales. You can see the mass scales indicated on the bottom axis here, and vice versa for models that enhance the power spectrum. So dwarf galaxies probe small, extremely nonlinear and largely unexplored scales. These error bars on the plot show the range of wave numbers over which we've actually directly measured the power spectrum through various probes. And dwarfs live in this region of the parameter space with wave numbers above 10 inverse megaparsecs or so, where we don't have model independent measurements, and therefore there's a wide range of dark matter physics that can be constrained. Now, on the other hand, dwarfs are also extremely useful for testing in situ dark matter physics. I'll give you a couple examples and then I'll come back to this in much more detail. But we can understand this, for example, by considering the scattering rate of self-interacting dark matter. So if you write down an expression for the number of times a particle scatters within the lifetime of the universe, then you can see that for a cross-section of order 1 centimeter squared per gram, dwarf galaxy halos, which, as I said, have masses of about 10 to the 9 solar masses and lower, will be significantly affected. And in particular, dwarfs probe relatively low scattering velocities between dark matter particles, which makes them complementary for SIDM constraints to, for example, galaxy clusters. And on the other hand, in the case of fuzzy dark matter, dwarf galaxy halos probe small scales that can be affected by wave interference. So the basic way to understand this is that the de Broglie wavelength in ultralight dark matter models is inversely proportional to the particle mass. So for particles with masses of the order 10 to the minus 22 electron volts, the de Broglie wavelength has a value of about a kiloparsec and therefore affects clustering on dwarf galaxy scales. Okay, so in terms of the constraints, I'd like to break down what I show you into two main probes. The first one I'll consider is the luminosity function of dwarf galaxies, basically the number of dwarf galaxies as a function of their luminosity. And the second one that I'll come to in the later part of the talk concerns the density profiles of the dwarf galaxies. So starting with the luminosity function, here I'm showing you an example for the Milky Way's satellite galaxy luminosity function. Of course, in the Milky Way, we can detect dwarfs down to extremely low luminosities, which makes it very useful. And there's a simple counting argument which gives you a sense of the halo mass sensitivity of this measurement. So in particular, if we take the total number of Milky Way satellite galaxies that have been detected, roughly 60 or so, this number can be corrected for incompleteness, which raises it to a few hundred. And we associate those galaxies in kind of a one-to-one fashion with the number of underlying subhalos predicted from numerical simulations. Then we conclude that subhalos with peak masses down to at least 10 to the 9 solar masses must host the observed Milky Way satellites. But this is actually a very kind of conservative argument in the sense that there are a large number of effects that actually push this limit to even lower masses. So for example, not every subhalo in the Milky Way is expected to form an observable galaxy. There might be large scatter in the connection between galaxies and their dark matter halos. There's the effect of tidal disruption from the Milky Way disk and so on. And combining all of these into a probabilistic inference pushes this limit down to a mass of 3 times 10 to the 8 solar masses, given the current data from the Dark Energy Survey and pan-stars. So with this halo mass sensitivity of roughly 10 to the 8 solar masses on the peak mass of any of the Milky Way satellites, we can then place a number of kind of competitive dark matter constraints. So I'd like to show you one example here from this Dark Energy Survey analysis, where we considered various models that imprint a cutoff in the linear matter power spectrum. That's the top left panel. Those cutoffs then propagate to an underabundance of subhalos relative to CDM. So this middle plot shows the suppression of the subhalo mass function relative to CDM. And finally, that results in an underabundance of the faintest satellites in the Milky Way. And importantly, this underabundance is robust even when marginalized over our uncertainties in the formation history of Milky Way and in the galaxy halo connection. So the lower limit on the warm dark matter mass that results from this analysis is 6.5 keV at 95% confidence. And this is complementary to Lyman alpha forest, strong lensing, stellar stream, and other limits in the literature. Now we can further translate this limit on the thermal relic warm dark matter mass into specific models. I'll show you a few examples of this. The first concerns sterile neutrino dark matter. And in particular, here I'm considering a mechanism where the sterile neutrino is resonantly produced. So this parameter space is the mass of the sterile neutrino on the x-axis and its mixing angle on the y-axis. And these blue and red shaded regions are ruled out as a result of this 6.5 keV warm dark matter constraint. And you can see that this parameter space is really tightly constrained by structure formation, particularly when combined with limits from lack of X-ray annihilation signal. Most or almost all of the parameter space for this particular model is ruled out. As one example, this 3.5 keV line from galaxy clusters is ruled out. The interpretation of this line as sterile neutrino dark matter annihilation is ruled out at extremely high confidence. So there's actually a more general way to frame these limits. Essentially, dark matter free streaming should not erase power on the scales that correspond to these 10 to the 8 solar mass halos. Okay, so coming to this example with interactions between dark matter and baryons, the basic idea is that if we introduce some new interaction, new non-gravitational scattering between dark matter and, for example, protons, this suppresses small-scale structure. And the reason is that the photon-baryon fluid transfers heat and momentum to the dark matter in the early universe. And this scattering actually completely freezes out well before recombination. So this is well described by a change to the initial conditions alone. So there's some examples here. The blue models have various cross sections for dark matter proton interactions. And in this particular case, the shape of the cutoff matches fairly well that of warm dark matter, which allows us to translate these limits. There's actually a simple analytic way to understand the scale of these cutoffs. They're essentially set by the size of the cosmic horizon when the momentum transfer rate freezes out relative to the Hubble rate. So if we take a look at the limits in this parameter space of dark matter mass versus dark matter proton scattering cross-section on the y-axis, we can see that the Milky Way satellite luminosity function improves limits from other cosmological probes by several orders of magnitude. And in fact, there are similar gains for models where dark matter scatters with electrons or with radiation, and also in various velocity-dependent scattering models. Now, interestingly, direct detection experiments, so terrestrial experiments on Earth, constrain exactly the same physics. So these are the classic experiments that have searched for WIMPs, but they generally constrain this parameter space at much higher dark matter mass, whereas the structure formation limits complement them at low dark matter mass. And once again, there's a general way to phrase these limits, essentially collisional damping due to dark matter standard model interactions should not erase these roughly 10 to the 8 solar mass halos that we observe in the Milky Way. And finally, I want to come to fuzzy dark matter. So actually, I'm going to return to this topic a few times throughout the talk. So if we take these limits from the Milky Way satellite luminosity function and map them to fuzzy dark matter using a semi-analytic model for the subhalo mass function in these scenarios, then we come up with a lower limit of 2.9 times 10 to the minus 21 electron volts at 95% confidence. And so this limit strongly disfavors the roughly 10 to the minus 22 electron volt models that could produce large cores in dwarf galaxies. And this is actually reminiscent of a similar situation for warm dark matter. So there's this lovely quote from a paper in 2012 in the context of warm dark matter. If you want to produce a large core inside of a halo, then that halo won't form at all. And so actually exactly the same kind of wisdom, I think, applies for fuzzy dark matter. Now, once again, in general, we can say that the Jeans length associated with dark matter wave interference should not erase power on the scales of these 10 to the 8 solar mass halos. All right, so the previous limits that I showed you were mainly based on previous generations of warm dark matter simulations, and in particular, the subhalo mass function suppression derived from those simulations. But of course, we want to do better than that. We'd like to actually directly model the signals as a function of the possible initial conditions for the subhalo populations in the Milky Way. So we've recently done this. This is a collaboration that I've led known as the Cosmic Simulations with my collaborators in Southern California. And we've considered a large number of possible initial conditions for warm, fuzzy, and interacting dark matter models, including models with large dark acoustic oscillations in the power spectrum, and self-consistently propagated those through to the corresponding halo and subhalo populations. So there's a few interesting results that come from this analysis. Now, returning to this question of fuzzy dark matter, what we find when we do the direct n-body simulations is that the subhalo mass function in fuzzy dark matter is suppressed relative to CDM with a shape that is significantly steeper than that in warm dark matter. And this actually directly reflects the underlying linear matter power spectra where the fuzzy dark matter transfer function cuts off more steeply. So this new subhalo mass function model that we derived significantly improves the limits on fuzzy dark matter from satellite counts, pushing it to 1.4 times 10 to the minus 20 electron volts. So almost an order of magnitude improvement just through more precise modeling of the underlying subhalo mass function. In Cosmic, we've also considered scenarios where there's a mixture of different dark matter components. So for example, some fraction of the dark matter might be warm and the rest of it might be cold. And these can be parameterized through a cutoff in the transfer function along with kind of a plateau where the height of the plateau, parameterized here by delta, tells you how much cold dark matter there is in a given model. So by running these simulations, we were again able to derive models for the subhalo mass function as a function of both this cutoff scale and the height of the plateau. And this yields limits on, for example, mixtures between cold and warm dark matter, shown here as the fraction of warm dark matter on the x-axis and the mass of warm dark matter on the y-axis. Now, this luminosity function probe only constrains these kind of mixed dark matter models down to roughly models with 50% warm dark matter. And below that, the current data does not probe the subhalo mass function with sufficient precision in order to put constraints. Before I move on to the density profiles of dwarfs, I just want to mention that these luminosity function bounds in principle can also be applied to constrain in situ dark matter physics. So for example, dark matter self-interactions or decays and other coring mechanisms can lead to complete subhalo disruption. You see a very nice example of this here from some of Rafael Arani's simulations where, if you initialize essentially the same system with either a cusp or a core and then let it orbit in a tidal field, the cored system can completely disrupt, whereas the cusp always survives. However, placing constraints on these scenarios through the luminosity function is much more challenging because the halos in question and their galaxies did form at some point, but later on disrupted, which means that we really have to understand this process of both halo and stellar disruption in order to place robust constraints. So I think this is a very interesting area for future work, and it could yield strong constraints, for example, on the SIDM cross-section. All right, so moving on to dwarf galaxy density profiles. The basic idea here is that if we can measure the inner profiles, both the amplitude and the slope of the dark matter halos that dwarf galaxies occupy, this can really incisively test physics beyond CDM. So you see an example here on the left-hand side from Kohei Hayashi's paper. The stellar to halo mass ratio is on the x-axis, and the inner slope of the dark matter profile is on the y-axis. And the idea is that for sufficiently faint systems, the predictions for the inner slope in a CDM context approach NFW, because there's essentially not enough energy from stellar feedback to core these systems in other ways. So in other words, the detection of cores in these extremely faint systems may point to physics beyond CDM. Now, the challenge here is that for many or even most observed dwarf galaxies, we only have typically a single velocity dispersion measurement in the very inner regions. So the half-light radii of these systems are typically smaller than a kiloparsec, which is a very small fraction of the virial radius of the dark matter halo. So in essence, these measurements constrain the enclosed mass at a very small scale, but there's large uncertainty when extrapolating that enclosed mass to an entire density profile. Nonetheless, there's been a lot of work in this direction in recent years. I'm going to show you a couple examples of constraints on ab initio physics, and then I'll come to the dark matter self-interactions. So in particular, if you change the power spectrum, so in a warm dark matter context, for example, this affects the formation times and therefore the concentrations of small halos, which systematically alters their velocity dispersions, their stellar velocity dispersions. And it's been shown that this mechanism can be used to constrain both suppressed power spectra. I'm showing an example here on the left where Stacy Kim derived a limit of roughly 6 keV from this mechanism, and also enhanced power spectra here on the right in the context of red and blue tilted primordial power spectra. Now, coming back to fuzzy dark matter, I mentioned earlier that there's this possibility of wave interference affecting density profiles on dwarf galaxy scales. In fact, one of the strongest constraints in the literature comes from dynamical heating. The idea is that fluctuations in the fuzzy dark matter field can heat the stars in ultrafaint dwarf galaxies, which increases their velocity dispersions. And a bound from this mechanism using the dwarf galaxies Segue 1 and 2 observed velocity dispersions and sizes places a lower limit on the fuzzy dark matter mass of 3 times 10 to the minus 19 electron volts, which is extremely strong. There have been lots of other analysis using dwarf galaxy profiles to constrain fuzzy dark matter. There was actually a paper just this week from Maria, which I'm showing here. And one really interesting outcome of these analyses is that fuzzy dark matter tends to predict larger cores in smaller dwarf galaxies. And this is actually contrary to the observed scaling of dwarf galaxies' core sizes. So as a result, these ultrafaint dwarf profiles place strong constraints on the fuzzy dark matter mass, and these are comparable to the limits from structure formation that I showed you before. All right, so finally coming to self-interacting dark matter. Typically, when we consider SIDM, actually for a long time, velocity-independent cross-sections were often considered. And the classic signature of these cross-sections is to produce density cores inside of halos. Therefore, the existence of even a single galaxy that has a cuspy density profile can be used to place strong constraints. So here's an example from Reed et al., where they used the Draco dwarf galaxy to place an upper limit on the effective cross-section at Draco's velocity scale of 0.57 centimeters squared per gram. And more recently, this has been extended to full populations of halos of satellite galaxies around the Milky Way. So I'm showing an example here comparing CDM and SIDM predictions for the enclosed inner density. And these authors derived an upper limit on the velocity independent SIDM cross-section of 1 centimeter squared per gram. Now, this classic SIDM story of coring is not the entire picture. So if you take an SIDM halo and you let it evolve for a sufficiently long time, after the core expansion phase where the central density decreases, it will enter what's known as the core collapse phase, where the central density actually increases in a runaway fashion. So with my collaborators, Daning Yang and Haibo Yu, we've actually implemented cross-sections where this core collapse can be achieved within a Hubble time, which typically have strong velocity dependence in order to avoid constraints from galaxy clusters. And we've implemented these in full n-body simulations of Milky Way analogs. So here are a couple of results from these analyses. I'm showing here circular velocity profiles of subhalos, simulated subhalos in a Milky Way analog in CDM on the left, and one of these strong velocity-dependent SIDM models on the right. And interestingly, you can see a few things. So first of all, this SIDM model increases the scatter in the predicted rotation curves, and also predicts the existence of extremely dense satellite and actually isolated dwarf galaxies. And so the outcome of this gravithermal evolution correlates with the halo's mass, its initial concentration, and also its orbit, as shown in the color code by the pericenter distance. So, this kind of dichotomy between ab initio and in situ physics is of course a bit artificial. There are many models where both kind of effects can occur. And actually in these velocity-dependent SIDM models, we also generally expect changes to the initial conditions for structure formation because there's typically a light mediator that is around and setting this velocity-dependent cross-section. So here's an example from the third cosmic paper where we combined these two effects, implementing both a change to the initial conditions, shown by the blue lines, in a self-consistent model that also produces a strong velocity-dependent SIDM cross-section. And this leads to the possibility of doing really interesting kind of multiple way comparisons, multidimensional comparisons between, CDM and a model with only SIDM or a model with only power spectrum suppression compared to both effects. The basic finding from this analysis is that this linear matter power spectrum suppression reduces the core collapse signature. This plot is showing a cumulative distribution of the gravithermal evolution timescale in a model with only SIDM in magenta, and then various amounts of power spectrum suppression in the blue shades. And there are two effects here. First of all, some of the low mass halos that would have core collapsed in SIDM don't form once the power spectrum suppression is introduced. And some of them that do form have substantially delayed growth, which pushes their core collapse timescale into a regime that's too long in order to actually observe it by redshift 0. Now, before I move on to the last part, I just want to mention that there are a couple intriguing puzzles that we have in the current data concerning dwarf galaxy profiles. So first of all, there have been specific systems observed that have unusual properties that are kind of contrary to our predictions in standard kind of CDM frameworks. For example, systems like the Crater 2 dwarf galaxy have extremely large sizes, despite being very cold. And this is difficult to explain just through tidal stripping in CDM. It's an open question whether, for example, baryonic feedback can produce systems that are as extreme as Crater 2. On the other hand, in the field, there have been isolated gas-rich ultra-diffuse dwarf galaxies observed to have extremely low inner circular velocities given their maximum circular velocity. In other words, the rotation curves rise extremely slowly. So in a CDM context, these would be interpreted as very low concentration halos. And we've shown in various papers that in, for example, SIDM models, these systems can be naturally produced. Again, it's an open question how to explain these systems through baryonic feedback alone. And now coming back to the dwarf galaxies around the Milky Way, there's an intriguing observation that several ultrafaints have universal stellar surface density profiles, which suggest cored inner dark matter profiles. And these systems should be below the limit where baryonic feedback affects their inner density profiles. They're too faint to be cored by feedback. And so observations like this really warrant scrutiny, I think, because if this holds up, then it could be a signal of physics beyond CDM. All right, just a couple slides at the end in future directions, and then I'll wrap up. So I've shown you results using current data, as I said, from the Dark Energy Survey and Pan-STARRS. There's a lot of exciting upcoming data, particularly from the Rubin Observatory. We expect that many more Milky Way satellites and dwarf galaxies throughout the local volume will be discovered in upcoming years. And we've done a kind of comprehensive set of forecasts to quantify the constraining power of these upcoming measurements, which is really quite exciting. So just to give you one example, if we combine two satellite galaxy populations, you can imagine all of the Milky Way satellites and all of M31 satellites, then the sensitivity to warm dark matter mass, the constraints can reach the level of 20 kiloelectron volts, which is really quite strong, even compared to the best current limits. One other direction, so the dwarf galaxy constraints that I've shown you are fundamentally kind of limited by the galaxy formation threshold. Dwarf galaxies can't occupy arbitrarily small halos. And therefore, one exciting way forward is to combine dwarf galaxy data with probes that are independent of the galaxy halo connection, for example, gravitational lensing. So this example I'm showing you here actually combines the posterior distributions on the warm dark matter mass and subhalo mass function amplitude that were derived from our Milky Way satellite analysis with those derived from an analysis of strong lensing flux ratio statistics on the left. And the point is that combining these kind of independent probes of small scale structure leads to stronger constraints. In this example, the 6.5 keV constraint that I showed you earlier improves to the level of 9.7 keV when combined with the strong lensing data. And so I think this kind of joint analysis is really the way forward. This will help us place the strongest constraints on the linear matter power spectrum, both in terms of possible cutoffs and enhancements. And just to mention, the upcoming strong lensing data is really very exciting. There have already been preliminary analyses of JWST flux ratios showing that they are sensitive to halos down to 10 to the 7, and maybe to some extent even down to 10 to the 6 solar masses. And the key point is that those masses are well below the canonical galaxy formation threshold inferred from our analysis of the Milky Way satellite population. In a sense, this means that combining these data with the upcoming dwarf galaxy discoveries will test whether completely dark halos exist. Okay, so just to recap here and then wrap up. So hopefully I convinced you dwarf galaxies are really crucial tests of dark matter physics. There are key areas for modeling work that can lead to improved constraints in the coming years. I mentioned a few, for example, luminosity function constraints on in situ dark matter physics, constraints on velocity-dependent SIDM, and joint analysis of satellite and isolated dwarf galaxies. And I think moving from this picture of this wide spectrum of constraints to actual dark matter discovery will require combining this dwarf galaxy data with independent probes, some of which I mentioned, strong lensing, for example. All right, thanks so much. I'll wrap up there.
Thank you, Ethan, so much for your wonderful talk. So please go to Padlet and then answer some questions addressed to you. Now let's move on to the last talk of this workshop, which is given by Manoj Kaplinghat. Manoj, can you hear me?
Yeah, I can hear you.
Hi. Great. Would you be able to share the screen?
Yeah, hold on.
Yeah. Excellent. So Manoj is from University of California, Irvine. He's going to tell us about SIDM, motivations and the viable signatures, please.
Can you hear me well, Shinichiro?
Yes, I can.
Okay, good. So Ethan's a hard act to follow, but also I think it's a really good introduction to, in some sense, to what I'm going to say. Well, I'll try and focus a little bit more on sort of the simplest models of SIDM and try to place them in the context of what I would call small scale structure puzzles. They've evolved over time. But before I start there, let me sort of like back up and at least give you my sense of like, the way I think about the models and the motivations. So I'll start a little bit about, talking about the motivations. And then like Ethan was talking about right at the end, this idea of like gravithermal collapse and large cross section. I'll try to motivate that and end with a couple of tests, but really, Ethan's covered most of these tests, so this will be sort of a very quick overview of the tests of these kinds of models. So just as the way I think about this is typically in a more general way with thinking about dark sector dark matter. And sort of the takeaways from this is that if we have a dark sector, there's no longer any need for the particles in the dark sector to be at very high masses. And that just opens up this idea that, you can have essentially interactions between dark sector particles that give you observable signatures, and that open up these astrophysical probes. So very quickly, this is sort of this is now 20 plus years of work. We know that to impact structure formation in galaxies, you need this elastic cross section over mass to be of order a barn per GeV or centimeters square per gram. And we also now know that the only way these kinds of models are going to be viable is if the cross section is enhanced at small velocities and decreases. This is not to say that those are the only models allowed, but these are sort of, it's going with this statement that you want to impact structure formation in galaxies. And if you do want to do that, then you need a large cross section at small velocities. And you cannot have that velocity, you cannot have a cross section that's large, even at large velocities. In addition, another reason to think about these dark sector dark matter ideas is that there are new mechanisms for producing this kind of dark matter. For example, freeze-in, which sort of uses this weak coupling between the standard model and the dark sector, or for sort of these kind of cannibal dark matter where you have these 3-to-2 interactions that in essence uses the fact that within the dark sector you can have strong interactions that lead to, for example, these 3-to-2 processes being dominant. So there's been there's a lot of interesting work from like various different areas that sort of motivate thinking more about these kinds of dark matter models. So just one quick slide is just to amplify this point at the bottom of the screen, which is that I won't come back to this, but just keep it at the back of your mind that we're always talking about, if you're thinking about elastic cross section, about models where the cross section is really can be large, 1, 10, 100 centimeters square per gram at small velocities, but then has to decrease when you go to larger velocities. Okay, so this is a huge parameter space, right? Like any way you look at it, much of it is probably ruled out, but there's a lot to investigate, and there's many ways to proceed. My focus here is just going to be to do a very simple thing, which is already hard, which is to look at elastic scattering between dark matter particles and then ask and try to pick out the parts of parameter space that actually have an impact on the small scale structure puzzles. No model on the market right now, whether it's of any kind, can claim to solve all of these puzzles. The idea here is to just ask, like, is this model ruled out, or is it still viable? And if so, does it impact the small scale structure? So in some sense, I'm using these small scale structure puzzles as lampposts. Okay. So in particular, there's two sort of general issues that I'll highlight. Ethan's already talked a lot about the diversity problem. So I'll just highlight that maybe from a slightly different perspective. And then what is really related, but sort of framed a little differently, this too big to fail problem. So let me skip to talking about the diversity problem. It was sort of popularized by Oman et al. With this really nice plot. And the key thing to take out of this is that the data points here on this plot, are showing you rotation curves of 4 different galaxies. And they all asymptote to sort of roughly the same velocity, around 80 kilometers per second. But the rise is very different in each system. And so when we talk about diversity, that's really what it means here is that if you think about the Vmax or the flat part of the rotation curve, that's roughly the same, which means roughly the same amount of baryons in these galaxies and maybe close to the same amount of dark matter mass. But then if you look at the inner regions, they look very different. Okay. This is something that's puzzled me since I started looking at this. And I just want to show you a plot from a little earlier where this is back in 2010, where we sort of plotted it in a different way. So here now you see on the x-axis Vmax, right? So that's sort of, for now, without worrying about the details, just think of that as the flat part of the rotation curve, which in most cases it is. And then on the y-axis, you see the core density. Okay, and the core density is essentially just the slope of this rotation curve in the inner part. So if you look at the slope, and I've drawn a line there for you in the fourth plot on the right plot, and if you just take draw a straight line there without worrying too much about what the details, that gives you an idea of the core density, and you can put that on the y-axis. And what's interesting is, so these are like 7 low surface brightness galaxies on the left. At around 70 or 80 kilometers per second, you can see that the core density varies by more, maybe close to orders of magnitude, but maybe a factor of 30 or 50. And so that is the essence of this idea, this puzzle, which is what gives rise to systems that are at the same Vmax, that are really dense, but also in other cases that are like extremely underdense. Okay. And these are all systems that, in this case, the ones we picked out on the plot on the left are all low surface brightness galaxies, right? So the galaxies, the stellar content by itself is not changing the dynamics, although feedback can. But just in terms of its gravity, the baryons are not that important. Here's another look at this diversity. And this is a little bit of a complicated plot, but I'm just going to focus on a couple of these panels. So for example, on the y-axis, so this is from a reasonably large compilation called the probes. And this paper the plots are from Frost et al. And so on the y-axis, you see this slope that I was talking about. Just if I go back to the previous plot, that's just the slope of the rotation velocity versus radius. And if you focus on the first plot on the x-axis, is just showing you the surface brightness. Okay. On the left, you have things that are low surface brightness here. And it may not look like much, but remember that the y-axis is a log. So 1 means essentially the rotation curve changes by 10 kilometers per second when you go out about a kpc. Whereas 2 would mean that the rotation curve has risen to 100 kilometers per second within a kpc, right? And so another way of looking at this diversity is just to see the spread in S at the same surface brightness. And it's a really huge spread. And this is just, again, talking about the same thing that was in the last slide, which is that, you get a couple of orders of magnitude, maybe, of spread. In the previous plot, it was at the fixed Vmax. Here, we are talking about, sort of fixed surface brightness. Okay. So, there are many different solutions that people are thinking about. One of them is that simply that the data is just wrong, right? That there's no code halos. The other one is that you have strong feedback. And the third one is different, dark matter models, right? An example could be like self-interacting dark matter. You can think about other ideas. Okay. So I'm going to talk more about this SIDM, but before we look at it, we need to really understand a little bit about how the self-interactions impact galaxies. Okay, so I'm going to show you something that's in the work. This is an example of there's no baryons in there. This is a DMO, the dark matter only simulation, but it's a simulation with a very large cross section, so 70 centimeters square per gram. And this is an isolated dwarf galaxy forming in a fully cosmological simulation. It's one of the fire initial conditions. And to zeroth order, what you can see is that it looks like any other CDM simulation you've seen, right? And I'll show you on the next slide that there are differences, but pretty much all the differences are relegated to the inner KPC, to a few KPC. And this is a fairly low mass system. It's a dwarf galaxy. Its virial mass is around 10 to the 10 solar masses. Okay. So I'll just play this once more down to Z of 0, and then this is the same galaxy, but I'm now showing you on the left what's happening to its density versus radius. So on the y-axis, you have density in solar masses per kpc cube. The x-axis is the radius from the center in kiloparsecs. And so you can see the galaxy is forming, sort of the outer NFW profile is being set, but then you can see it's a big core, about a kpc, couple of kpc. And now you can see that the core density starts rising towards the end. I'll let this play out again. So right at the end, you see the core density start to rise. Initially, you saw that the core forms and the core size keeps increasing. And this is just the thermal transport of heat from the outer part of the halo to the inner part of the halo. If the cross section is large enough, the life cycle of these SIDM halos kind of looks like this. It doesn't always have to look like it, but this is an example where you haven't had too many mergers. It's a relatively quiet life for this galaxy, and it's happily gone through this process of like forming a core, and then the core starts collapsing in the sense of like the density increasing in the center. You can put this on sort of a phase space plot here. This gives you an idea of like, sort of what happens. So on the y-axis is the core density. So, if you want just the flat part of the density profile right at the center, it's normalized to rho s, which would be sort of if you take the outer parts and just fit an NFW profile to it, because the outer part looks NFW, then you take the rho s of that NFW profile, and so you sort of normalize it that way. And the x-axis is essentially the dispersion at the center of the velocity dispersion, normalized to Vmax of the halo. And for most models, and there's a whole bunch of different models here. The difference between the different lines, I don't want to go into it right now, but you can sort of see an envelope where you start out more or less NFW on the left side. And then as time goes on, the inner part heats up and the density starts falling. Okay. And then it reaches sort of a minimum density at a particular characteristic dispersion around 0.65 times Vmax, and that seems to be really robust, doesn't really change very much. And then after that, the core starts shrinking. So the core size reaches a maximum of around 0.4 or 0.5 times RS. And then beyond that, the core size cannot increase for very good reasons. And then the core starts shrinking and the density starts increasing. And this process, the halo goes through this, increasing density transition. And this happens for, like I said, most isolated halos will go through a transition like this. The key thing to note is that most of the time is spent right around that, the minimum. And so on the x-axis on the top, right? So you can see the time in some dimensionless units, and you can see that the most of the time, which let's say is from -40 to 300, is spent in this phase where the core is like fairly large and the core density is fairly low. Okay, so one quick takeaway from this whole thing is that if in sort of field halos, even if core collapse happens, it's not going to be something very, very common. There will be a lot of core halos floating around in any of these models. Okay, and so here's another way of looking at it. That I'll use this plot again. This is now plotting the core density, so rho C over rho S in these dimensionless units versus time, rather than, in the previous plot, I had plotted the velocity dispersion, which actually is a very good indicator of time. As long as the velocity dispersion is increasing, which happens for isolated halos, it's essentially just, like a clock. But here, this is just plotting it versus time. And this is what I was alluding to before, which is that for a huge range in time, right, which if I basically the core density doesn't really change very much. Now the x-axis here is not actually time, it's time in these scale units, and there's a TC0 listed there, that scale. And that TC0 or the inverse of that is essentially the rate at which these interactions are happening. Okay. And that's proportional to essentially the core density times the velocity dispersion in the core. So rho C0 and VC0 are the values here. Times a cross section that's funnily averaged, and I don't want to go into this now, but there's a particular averaging that seems to end up giving you back what we see in the simulations. That there's some theory behind this, but really in the long mean free path, we still don't know why this works, but it does work reasonably well for a good set of the velocity-dependent models we've looked at. But for now, we can talk more about this in the session later. But for now, just think of this as like some effective cross-section, right? And so if you have a fixed time, then the x-axis is also telling you something about the cross-section, right? As I keep increasing the cross-section, you move to the right. And I've highlighted this box in orange to say that essentially there's like very good analytic model for predicting what the density profile in these SIDM halos should be. And that might seem funny because in CDM, it's hard to do because of baryons. And the reason why you can do it in SIDM is simply that, there's really one way to be in equilibrium. And once you drive towards that equilibrium, or at least a big part of the halo gets close to thermal equilibrium, it becomes very predictive. So it's a very predictive part of the model space. And eventually this part of the model space is actually not going to work, is what I'm going to tell you in the next a few minutes or so. So because you have this analytic model, you can go ahead and ask is this a viable part of parameter space to explain the diversity problem? And we did this now a few years ago with, and what we found, so this is a paper, I forgot to cite it here, but this is Haibo and me and our groups. Like what we showed is that you can get pretty good fits across the range for essentially most of the galaxies in the Spark sample. Okay, now there are problems with this, and I'm going to talk about that next. But if you just zoom out, by and large, what you're saying is that there's very different variations from galaxy to galaxy in the rotation curve, and there's a very simple model that gets to first order these variations. So that's really encouraging, right? So that's what I mean by saying this is a lamppost. You found a parameter space where things seem to work. Now, whether they work in detail or not, that's a different question, but they seem to work, and it's a good one to look at more. Okay, and you might ask, well, where is this diversity coming from? And it's coming from two sources. One is really this halo concentration, and then the other one is the stellar distribution. They both impact the rotation curves. Now, there's a lot of galaxies here. If you pull out the galaxies, some of the galaxies that are low surface brightness, you can see that, here's a set of I forget how many there are, but a dozen or so galaxies that are really low surface brightness. But you can see they have all kinds of shapes. And in particular, focus on that sort of the purplish points that rise really quickly, okay? When they rise quickly, what that really means is the surface, the dark matter central density is very high, which means that the core size is very small. So this is what Ethan was alluding to, which is that, if you just keep making cores all over the place, you're going to be ruled out, right? No such model is going to work. And the plot on the right is just harking back to that 2010 paper I was talking about, which is plotting the central density versus Vmax. And again, you can see the same thing, which is at about 60, maybe 70 to 80 kilometers per second, the central densities have this 1.5 orders of magnitude spread, right? And so the key question is that in this plot here I was showing you, there are galaxies like that. How did we get things to rise so fast? And the bottom line is that some of those galaxies are outliers here, and they're outliers in a very specific way. So for example, if I take a cross section of 3 centimeters square per gram and look at the fits, then you get on the x-axis, you get the central density in dark matter, and you see the same range, about 2 orders of magnitude. And on the x-axis here, I'm showing you what concentration do you need to assume to get it right. And it's been normalized to sort of the median concentration that you get in CDM, which is a pretty good approximation for SIDM in at least these models. And really you can see what's happening is that you got to push up a lot of these low surface brightness galaxies to the right, which is essentially saying that, these low surface brightness galaxies need to be sort of sampling the high end of the tail of the concentration distribution. So when you look at 135 galaxies, 150 like we did there, it doesn't seem like much, right? I mean, you expect outliers, but when you just focus in on these LSBs, this becomes a worrying trend. And so you can ask yourself, well, is there a way out? And the alternative is that, you were focusing on sort of this plot of density versus time and looking at systems that are, you remember, sort of on the left side of this plot, more or less. But you can ask, why can't we be on the right side of this plot by increasing the cross section? And so we did this recently, and what we found is that essentially all of the success that we found with 3 centimeters square per gram was recovered. But in addition, you can get these really nice fits with 40 centimeters square per gram, where the concentrations don't have to be, crazy high, like at the, 0.3 dex and higher, right? So this is a clue that, you can look at much higher cross sections, like 40 centimeters square per gram, 50, 60, maybe up to 100. Now there'll be some point where you hit maybe 200 or 300, where what will tend to happen is that all the, you won't form cores in these galaxies. You might tend to just have them all look like very core collapsed halos, and that might not be consistent. That upper limit hasn't been set yet, but eventually when someone does it, I think there will be an upper limit, but sort of in this ballpark of 40 or 100 centimeters square per gram at low velocities seems like a really good place to explore. Okay, so I'm going to maybe like 5-7 minutes, I'm going to quickly try to talk through a couple of tests of these things. So I'm running low on time, so I'm going to I want to talk about one specific thought about looking at satellites. So again, like Ethan talked about satellite galaxies in detail. The key difference between satellite galaxies and field galaxies, which I think is where you're going to get the constraints from in these models, is that if you look at the core density versus time plot, then it's going to depend on a lot of factors that don't exist for field galaxies. One in particular is mass loss. Okay, now this can go both ways. It can hurt you in terms of like, being more viable, and it can help you, right? So I'm just going to give you an example where you have mass loss through tidal stripping, and what that does is it sort of like accelerates the core collapse process. And I think this is a key feature in in these simple elastic SIDM models that's predictive, and we want to search for and see what that does to, let's say, the density profiles of the satellites, right? And because it's correlated with mass loss, it becomes very interesting to ask what the phase space of this effect is for satellites. So the plot on the right is essentially trying to break this down and say to take two of these variables. Now there are many more variables for satellites. Satellites are complicated, but it takes two variables. One is concentration. So the columns in the figures on the right are showing you high concentration and low concentration. So high concentration on the left and then low concentration on the right. And then the rows are showing you how close the satellite comes to the center of the host, right? So in the top row, they come close, and in the bottom row, they stay far away. And you can see very different behaviors, okay? So the three models that are shown are CDM, and then a moderate cross-section, and something that's large. And we've jacked up the concentration here. So even at 10 centimeters square per gram, you can see core collapse. So that's the red dashed line in these models. Okay. But if they come too close and they have low concentration, then the large cross-section doesn't help you. I mean, you basically destroy these galaxies. And that's what Ethan was talking about. If you just form a core before you even fall in, and you basically strip it, and this is old work from Jorge Penarrubia, you're just going to essentially obliterate the galaxy, right? So it's a very interesting phase space where some things will survive, some things won't. And it's correlated with the orbit of the satellite and its formation time, okay? And so I just want to show you this plot from which Ethan didn't show, but from his paper, where so you might ask, well, for these kinds of models where you have large cross sections, what's the part of parameter space that looks different from CDM? So here's a plot from Ethan's paper showing you Vmax, Rmax for the subhalos in one of his DMO simulations. And on the right is one of these velocity-dependent models where the cross-section is really large at small velocities. And there's two differences to notice. One is that you get, if you focus on the few dots that make it very high in Rmax, these are really puffy halos. Okay, in some cases these halos have been destroyed, but some of these are left over, which are what you see here. And so there might be corresponding signature in the stellar profiles too, where you get these really puffy extended things that somehow survive, and you can see them. There aren't going to be too many, but there'll be a few, and we see some of them in the satellite ultra-faint satellite data. But then also interestingly, because of core collapse, right? Because of this process where you're losing mass, and that sort of accelerates this core collapse. You see systems with very low Rmax. So these are really compact systems, right? And there again might be a signature not just in the velocity dispersion profiles, but also in the stellar profiles of these systems, right? So it's early days. There's going to be a lot more work in this area. I don't think the predictions are anywhere where they need to be to make sort of really informed constraints. But this is exciting because it shows you that these models kind of sort of look like CDM, but then have this sort of wings where you have more diversity, right? And it's good that they look like CDM because to zeroth order, even with all the cores and everything else there, the simple CDM model does amazingly well, right? And so if you want to focus on the differences, we'll have to look in the tails. We'll have to look for these like collapsed objects or these extremely dense things and take a very close look at them. Okay. So let me end with just talking a little bit about where else can we look for this? Well, if there are these collapsed subhalos, then they should be not just in the Milky Way, but they should be in galaxies that you should be able to see them in galaxy lensing. This is something is also hard to do, but it's I think one of these things that we'll have more data on in the next few years. So the idea here is basically to look at astrometric perturbations in the lensed images of background galaxies with limited resolution. So for example, with this 0.4 arcsecond resolution image, you're not able to see much, but at the bottom, you see something that you can see with radio. You can really map out these structures in there and then ask, where do these, in the images, where do the structures come from? It's a complicated thing to do, but there's only a few systems like this floating around, and this is what this is the last slide before I wrap up. This is an example of something that's been known for a while. This is Simona Vigeri's work from a while back. Basically, I'm showing you on the left an HST masked image of a galaxy lensing, and it's hard to tell by eye, but there's actually perturbations in that lens, and many people have gone back and looked at this, and every single time you recover that there is a subhalo, and the subhalo is about right there. Now after having looked at it for so long, I can convince myself that I can see it by eye. But really, I mean, this is just something you just have to do a likelihood test for it. And so the subhalo is, where that critical curve, the black line I'm showing you, kinks, that's the location. And the interesting thing about this image is that kink is very compact. And so what that's telling you is that there is actually a perturber there that's compact. And you can ask, well, what is the mass of the perturber? How compact it is? And the plot on the right is showing you an example of a very detailed analysis, giving you, both the background galaxy and the perturber and other things a lot of freedom. It's certainly not the final, and there's been a lot more work after we put this out. But this is kind of an example that I'm excited about, where the field can go. And so what this is showing you is on the y-axis, it's the slope of the recovered density profile at 1 kiloparsec. Now, this is the slope of the 2D density profile. So if you're looking for 3D, just -1 would be -2 roughly. So essentially -1 is like a 1 over r squared profile in 3D. On the x-axis is the mass enclosed within 1 kpc. So it's sort of a mass slope plot. And this perturber that's there in this system lies where that magenta contours are. Okay, so it's a mass enclosed within 1 kpc, about 3 to 4 times 10 to the 9 solar masses. So it's fairly massive. The baryons are like, I forget what the number is, but I think it's a few times 10 to the 7 or a little bit more of that order. So the baryons are not important here. And the slope is fairly steep. And if, we took a bunch of points from illustrators, did a lot of things to it to like make sure that, we pick out the things that are the most dense. And the key point is that, most of these points from illustrators, those are those magenta points in the background, lie up there, right? And so if you have a few systems like this and we do, really hard work on them, this may be one way to reveal these collapsed halos. And there's been some more work from Cora Dworkin and a group showing that there may be other systems floating around like this that similarly have large slopes. So the plot on the right here is a slope and a likelihood plot for it. And here now the slope isn't, I'm so sorry, it's actually the 3D slope with a minus sign taken out. So roughly speaking, the -1 on my plot here would be a 2 there, right? So to the right, it's much more steeper. And so the NFW expectations are around, are shown by the sort of light blue here, and then a truncated NFW expectations, they get, steeper, so somewhere there. And the inferred from a few of these systems is to the right, okay? And like I said, this is not, the final word on this, but this is an example of something exciting where you might be able to tell that there are things in the data that are denser than expected, both from the satellites and from lensing, and then probe this part of parameter space, right? So I'll just leave you with this, with a simple idea that in this limited scope, but still an exciting one, where I've looked at the lamppost being the small scale structure issues. There's an idea that you can find things that are denser than CDM, whether it's through lensing or it's through like dwarf galaxies in the field, or it's like satellites, galaxies. And that anomalously high density can then be turned into something that tells you, what the dark force mediator is. So for example, it's MEV or it's, lighter. And maybe then, that opens up an avenue for terrestrial experiments. So on that sort of optimistic note, I'll stop and take questions. Thank you.
Thank you. Thank you so much, Manoj, for this wonderful talk. We are going to have a discussion session after this. So first of all, we are going to close this Zoom link, and then you are all directed to the what's called the lobby, and then you have to click another link to get to the discussion room. So please do so, and all the question will be asked there, and then especially on the Padlet. Manoj, for example, if you go to Padlet, and then there are some already couple of questions for you posted, so please answer them on the Padlet. That would be best given the time remaining. So in the discussion session, before that, we are going to have like 10-minute break. And then at the discussion sessions, we are going to have a, first discussion that the organizers together with some speakers prepared, and that will be moderated by Diego. And then if we have remaining time, we can have some Q&A. So I think if you go to the the email and then click the link, you are directed to the lobby. If you are not, but then we'll meet there. So is everything clear? At least for the speakers? Yeah. So anyway, I guess we'll close this Zoom. Yeah. Okay. Thank you. Thank you, everyone. Yeah, same link. Thank you, everyone, all the speakers, for your great talks, and then we'll see you soon in 10 minutes time. Thank you.